Good evening, everyone. So we are back to the topic. We were on cells in the last class, right? Okay. Now this is a cell. A cell. This line is positive terminal and the smaller line is negative terminal, right? Okay. The EMF of the cell is called E1 and the internal resistance is called R1. What is internal resistance? It is a resistance inside the cell. Resistance inside the cell. Okay. Every cell has a inbuilt resistance. That is called internal resistance of the cell. Okay, right. And I got another cell here, which is also having internal resistance. That is R2. This is EMF is E2. And I'm going to connect them in parallel like this. All right. And then what's happening? Look at this. Like I told you yesterday, from the positive of cell, a current is being driven. That is I1. From the positive of second cell, we got another current I2. They join together to become a current I. Correct. It is parallel combination. And we even learned the effective of these combination. Effective of this combination. What is the equation for equivalent EMF? Equivalent EMF for effective EMF is given by E1R2 plus, tell me, E2R1 divided by R1 plus R2. R1 plus R2. That is how you find the effective EMF. All right. I repeat one more time. I'll tell you the context. We have two cells here. Cell number one is EMF E1. Internal resistance is R1. Cell number 2 is EMF E2. Internal resistance R2. And they are connected in parallel here. Parallel means positives are connected together. Negatives are connected together, right? Positive and negative are connected together. Such a combination is called parallel combination. Parallel combination. Okay. Now what? There is a current coming out of first cell, which is I1. Second cell also drives a current, that is I2. They join to become I here. Right. This is the context. And I told you about this. The effective EMF is given by E1R2 plus E2R1 divided by R1 plus R2. First cell's EMF into internal resistance of second one plus second cell's EMF into internal resistance of first one divided by sum of internal resistances. All right. But once there was a question, they interchange the polarities. One cell was taken this way, plus and minus. Second cell was given this way, just the opposite, minus and plus. What will you do then? Just make it E1R2 minus E2R1. E1R2 minus E2R1. If opposite polarities are connected together, opposite polarities. Look at this. In this case, which all polarities are connected? Positive is connected to positive, right? This is called parallel connection. Got it? But on the other hand, if you got something like this, positive of one cell to negative of the other cell, you will have E1R2 minus E2R1 by R1 plus R2. All right. Now, this is the parallel combination case. Okay. And second thing, we even wrote internal resistance equivalent. What is it? R1, R2 divided by R1 plus R2. It is common sense because it is what? It is parallel combination. Parallel combination effective is R1, R2 divided by R1 plus R2. All right. Now, this is what we learned in the yesterday's class. And one more thing, potential difference is given by EMF minus I into R. This is the equation for a cell. EMF of the cell is E. V is called terminal potential difference. There is one thing that I missed yesterday. I'll be doing it now. All right. So that's the end of cell part. Okay. I repeat one more time. We have a parallel combination of cells. And what is the effective EMF? Effective of those two, E1R2 plus E2R1 divided by R1 plus R2. All right. And effective equivalent resistance is given by R1R2 divided by R1 plus R2. And for a cell, we have an equation of this kind. V is equal to E minus IR. V is equal to E minus IR. All right. This is the first equation. This is the second equation. This is the third equation. Now, let me ask you one question. What if I take this equation and if I'm asked to draw the graph, look at this. This looks like Y is equal to C plus mx. Do you remember having seen this equation? It is a straight line, right? Y is equal to, I've told you many times, in class 12, we have only one equation, mathematical equation, which is the equation for a straight line. Y is equal to C plus mx. y is equal to c plus mx. All right. Y is equal to mx plus c. Choice of variable is mine. I'm going to take what? Look at this yellow circle. Look at this yellow circle. What is in place of yellow circle? It is current, which means I'm planning to take I on the x-axis. Understood? I'm planning to take current on the x-axis. Got it? Then what else? Look at this green circle. What am I going to take on y-axis? Terminal potential difference or voltage on y-axis. Got it? And I'm going to get a straight line, right? Because this equation stands for a straight line. I repeat one more time. This is very important. So many times as I missed it yesterday. Should have been written as a note yesterday. We wrote few notes. This is one of the notes. Repeated question. All right. V is equal to E minus IR. Right below this, we write Y is equal to mx plus C. Y is equal to mx plus C, right? Okay. So in place of X, I have current. In place of Y, I have voltage. So see the graph. I'm going to draw the graph now. Look at the graph. This is my graph. Okay, this is my graph. Y-axis and x-axis. And tell me about the graph. On the y-axis, I must take terminal potential difference, V. Correct. And on the x-axis, what should I take? On the x-axis, I should take current. All right. All right. What is the graph? What is the graph you expect? You expect a straight line, right? What kind of straight line? Look at the slope of the graph, M. Slope of the graph is internal distance, right? But it is minus, right? Minus means it's descending graph, right? Oh, I've told you many times. If you see the slope positive, it's going up. It's an ascending graph. Ascending graph. Got it? If the slope is negative, it is descending graph. All right. Now look at this and tell me, in place of M, we got R, or rather minus R, right? Minus R means it's decreasing. All right. So this is the graph I would expect. Okay, I would expect. All right. Now, can you see the paper? The paper? Can you see the question number 3 on the paper? All of you online? All of you online? Do you see the paper? All right. So, look at this. We have the question here. The graph is obviously a straight line, but as you can see, the slope is negative. Got it? Slope is negative means it's a descending graph. With which we are going to do question number 3. That is one of the most repeated questions ever. All right. I'll tell you an easy method to solve this question. 100% sure. From this paper, you will have one question in board examination and in your school examination. All right. Okay. 3 marks to 5 marks. Okay. Let's do. All of you write this down. Write this down. Write this down. Whatever you have written. This is actually coming from yesterday's class. But anyway, just write this down. All these cases. Okay. E equivalent is E1R2 plus E2R1 divided by R1 plus R2. E1R2 plus E2R1 divided by R1 plus R2. Second is R equivalent. We're going to do questions on this now. Equivalent resistance is R1R2 divided by R1 plus R2. Okay. Now mark this as very important. This is a very important point. You can write it as a note if you want. Yesterday we wrote few notes. You have to attach this to this. All right. So look at this. I chose to put V on y-axis, current on x-axis. Don't worry, they'll give that in the graph. All right. Oh, yeah, I'll write it. I would send, right? Okay, right. Right. You finish this. V is equal, thanks for reminding. Okay. V is equal to E minus IR. Y is equal to C plus XM, right? C plus XM. Now, what is in place of X? On the x-axis, we have current. On the y-axis, we have voltage, right? And the graph is obviously a straight line. Why is the graph a straight line? Because this equation represents a straight line. Correct. This equation stands for a straight line. And it is downward because the slope is negative. Okay. All right. Let us do a couple of questions. Now, can you take the paper? Let's do question number 2 and 3. 3, we will start off with question number 3. I'll do questions randomly. Question number 3. Okay, question number 3. Take the paper. You finished writing, all of you online? Could somebody please tell me? Question number 3. Take question number 3. Read the question. The following graph shows, mark it as very important. The following graph shows the variation of terminal potential difference V across a combination of 3 cells in series to a resistor versus current. Okay, calculate the EMF of each cell. For what current I will the power dissipation of the circuit be maximum? I'll tell you. Draw the figure. Draw the figure. I need to tell you a couple of more points. Draw this. Draw the graph. Voltage here and current here. All right. Then you can draw the graph this way. It's coming down from 6 and it's going to this point. Okay. So this location is like 1 ampere. This is 2 amperes, 0 ampere. Right in the middle, you got 3 and this is 6. Draw the figure. I'll explain this. Finish drawing this? Okay. Now I'll tell you, before I start, I'll tell you a couple of points. Look at this. First thing is, you got to find out what? You got to find out the EMF of each cell. For what current will the power dissipation be maximum? Look at this. Point number 1. This is called a series combination. Series combination of cells. Okay. Why is it called series? Because negative of one cell is connected to positive of the next. They are connected one after the other, right? For series combination, the effective EMF will be N times E. For example, yesterday I told you this remote has 2 cells inside. Why? Because the remote works on 3 volts. One cell is 1.5 volt. Okay, so 1.5 plus 1.5 is 3, right? If you need like 6 volts for like your laptop needs 12 volts. 12 volts if you need, you will connect how many cells? 12 by 1.5 is 8 cells in series. Got it? So the point is very simple. When N cells are connected in series, the effective is given by N times C. What if they are connected in parallel like this? What if they are connected in parallel like this? Whatever be the number of cells, the effective will be only due to one cell. Only due to one cell. I wrote this equation for what? For different EMFs, right? Different EMFs. Am I correct? Look at that. The first one's EMF was E1. Second one's EMF was E2. In that case, you call E1 R2 plus E2 R1 divided by R1 plus R2. But in case you have identical cells, everyone is E, you go on like this. Even if you have a billion cells, you will effectively have only one cell. If you have any doubt, try this at home today. Take a cell. This is the cell. There is a button at the top, which is positive. Another cell by its side, button. Another cell by its side. Then connect all the positives together, connect all the negatives together. This is called parallel combination. And connect a bulb to this. Even if you increase the cells, bulb will glow with same intensity. Okay, the bulb will have same brightness. All right. Even if you put one cell, 10 cells, 100 cells, or even a million cells for that matter, you would still have what? Same brightness for the bulb. Got it? What does it indicate? In parallel combination, number of cells is irrelevant. Number of cells is irrelevant. Okay, I repeat one more time. In series combination of cells, look at this. In series combination of cells, EMF is given by number of cells into EMF of one cell. In parallel combination, only one cell's EMF will be counted. Okay, that is point number 1. Point number 2, look at this context. I told you yesterday, this is the cell, this is the external resistance, and this is the internal resistance. All right. And this is EMF. There is something called maximum power transfer theorem, which is not mentioned in the syllabus anymore, but it still has a chance of coming in exams. Maximum power transfer theorem. Maximum power transfer theorem. From the name itself, it is clear. What is it regarding? Power transferred is maximum. Power transferred from the cell to the resistor is maximum when external resistance is equal to internal resistance. You don't have to prove it because the proof is that used to be there, it is deleted now. You use the principles of differentiation. There is something called condition for maxima minima. You will use to get this condition. But just know one thing, in a cell, if you want to get maximum power, what is the condition? External resistance should be equal to internal resistance. I repeat one more time, external resistance is equal to internal resistance. In that case, power, power is given by this formula. This is called Joule's law of heating. Power is equal to E square by R, right? E square by R, right? Power, we learned 3 equations in class 10. Power is equal to I square into R. Power is equal to V square by R. Power is equal to V into I. This is called Joule's law of heating. Correct? I'm using this equation. How to write power there? Power is equal to V square. V square is what? E square by resistance is what? R plus R. In case they ask for this condition, maximum power transfer theorem, you put capital R is equal to small letter r, or small letter r is equal to capital letter R. So you can replace this with capital letter R. What do we get? E square divided by 2 times capital letter R. Got it? Okay, so keep these points in mind. I'm going to do this question now. First of all, look at this equation. I'm writing my equation. V is equal to E minus IR. V is equal to E minus IR. Okay, V is equal to E minus IR. Now, tell me, what are the coordinates of this point? I can say it is 0, 6. Am I correct? Look at this. This is 0, 6. Why? The x coordinate is 0, y coordinate is 6. Right? 0, 6. What is 0 in this? Can you tell me what is 0? X coordinate. X coordinate is current, right? X coordinate is current, right? And what is y coordinate? Y coordinate is voltage. Am I correct? Similar way, how about this point? This point may be called 2, 0. Right? If you check internet for solutions, you will see complex solutions. But this is the best way to do it. It's class 6 mathematics. Okay? You know how to find the coordinates, right? You learned this in lower classes. This coordinate is 0, 6. 0, 6. Which means the first variable is I. X coordinate is I. Y coordinate is V. 0, 6. And here x coordinate is I. And y coordinate is V. All right. Into this equation, I put this condition. Tell me what you get. What is V there? What is V there? 6 is equal to E minus I is 0 into R. Correct? So you get what? E is equal to 6. Okay. They say that there are 3 cells in the equation. 3 cells. 3 cells. So this must be E equivalent, right? In the question, they say there are 3 cells. So I can call it 3 times E is equal to 6. So 1 cell's EMF will be what? 6 divided by 3, that is equal to 2. That is equal to 2. That is how I find the EMF due to a single cell. Because the EMF I get here is due to how many cells? They say that it is 3 cells. This question got repeated many times with the different values. All right. I retained only one question here. All right, as sample. Then what? Now I'm going to put this condition. I'll write that equation one more time. What is my equation? V is equal to E minus IR. I put the value. What is V from there? Tell me. Tell me, Vedant. V is what? V is 0. Is equal to E already I got it from here. E is how much? 6 minus I is what? 2 into internal resistance R, right? Now get this 2R left hand side. 2R is equal to 6 or R is equal to 3. Correct. This is actually the internal resistance of 3 cells, right? I said 3 cell in the question, right? So 1 cell gets how much? 1 ohm. So internal resistance of 1 cell is how much? That is equal to 1 ohm. See how simple the question is. Understood? Nothing embarrassed. You know, V is equal to E minus IR. I am putting this coordinate, 2, 0, that point. So what is I value there? I value is 2 from it, right? I value I am putting 2. Internal resistance is how much? Internal resistance is to be calculated. EMF is how much? I already got it. 6. Correct. I am putting it here, 6. So V is what? V is 0 there, right? We put them and then solve it. You get R is equal to 3. This is actually internal resistance of how many cells? 3 cells in series. All right. All right. 3 pen costs 3 reals. What is the cost of 1 pen? 3 by 3, right? Same way, right? 3 cells have an internal resistance of 3. 1 cell will have how much? 3 by 3. That is equal to 1 ohm. Got it? And in the second part, they're asking what? For what current I will the power dissipation be maximum? Current is what? This also we wrote yesterday. E by R plus R. Okay, current is equal to E divided by R plus R. For maximum power, I told you, what does the power transfer theorem say? Small letter r becomes capital letter R. So what are you going to get? E divided by R plus R is equal to 2R. Got it? E divided by 2R. You can put the value if you want. All right. So let us write it. I'll do it one more time. All of you understood this? Everyone online? Let us just write this. Tell me, write this. You can write a note. Write one more note, okay? Write one more note. In series, E is equal to N times E1. All of you understood this? All of you understood? Okay, right. In series combination, what is the effective EMF? N into E1. For example, one cell is 1.5, 2 cells will be 2 into 1.5, 3 cells will be 3 into 1.5, 10 cells will be 10 into 1.5. Got it? So depending upon your requirement, you can add more and more cells. Got it? Now, right, in parallel, you can try this at home today. E is equal to what? E is equal to, no matter what you have, even if you have a billion cells, only one cell will show up in the end. Understood? Understood? You will need this later on in another chapter also, this concept. That time I'll ask. Okay, even if you have 100 cells, 1000 cells, 10,000 cells, or 100,000 cells, effectively, we will have only one cell. What you will get is only 1.5 volt. Okay. So I'll repeat one more time. In series combination, number of cells into EMF of one cell. In parallel combination, only one cell. Again, in series combination, EMF of one cell into number of cells. In parallel combination, EMF of one cell alone. Okay, right. So note number 2, right? Note number 2. Maximum power transfer theorem. Many teachers do not teach this anymore, but you learn this because a couple of years back it was asked. Maximum power transfer theorem. Maximum power transfer theorem. From the name itself, it is clear. It's talking about the power transfer, right? Draw the figure. This is the cell. This is the external resistance. This is the internal resistance. Okay. Actually, I'm supposed to draw internal resistance inside the cell, but this is how it is schematically represented. All right. Put the current. The current is coming out of it. The EMF is E. EMF is another name for voltage. Okay. EMF is E. Yeah, maximum power transfer theorem. I'll tell you the statement of theorem only. Okay. You can write power transferred is maximum. Power transferred is maximum when you won't need the proof. Trust me on that. R is equal to R. This is the condition. We used to derive this like at 15 years back, but it is not needed anymore. All right. Power transferred is maximum when external resistance is equal to internal resistance. Could you please say that again? External resistance is equal to internal resistance. Got it? If this is 3 ohm, this should be 3 ohm. Then the power delivered will be maximum. Got it? Right. Also write the current then. Current is equal to E by, current is what? How to get current from this? Ohm's law. Current is Ohm's law. We ohm. EMF divided by total resistance is R plus R. Correct? Current is equal to E divided by R plus R. Okay. Also write the power. We will need it. E square divided by, what is the power equation? E square by R. E square by R. Power equation is E square divided by R. E square by R plus R. It depends on the question. Sometimes they'll give you internal resistance. So instead of capital letter R, you put internal resistance. All right. Some other cases, they'll give you external resistance. So you put small letter r is equal to capital letter R. For the example, this question has internal resistance. External resistance is not given. Got it? So we will put what? In place of capital letter R, you put small letter r. Got it? Then we will substitute and find out. Okay? Right. Now let us do the question. All of you got this point? Everyone? The last slide. If anybody, oh, we are writing this question. We haven't written this, Yusuf. You can just write the question. Question number 3. Draw the figure. Did you draw the figure, the y-axis and x-axis? Draw this y-axis, draw the y-axis, and draw the y-axis and x-axis. This is x-axis, okay? Right. And draw the graph. I'm drawing the graph now this way. I'm drawing the graph this way. Draw this. And I'm going to put the points. This point is like 1 ampere. This is 2 amperes, 0. This is like 3. This is like 6. All right. And on the y-axis, we have taken V. On the x-axis, we have taken current. All right. So what is the first thing you're going to do? You're going to do? Look at this. This point is like 0, 6. Am I correct? That location is 0, 6, right? Y coordinate is 6. X coordinate is 0. Now this location is what? It is 2, 0. 2, 0. Right there, tell me which all things are given. This is the x coordinate. Who is x coordinate? I. X coordinate is I. Who is y coordinate? Y coordinate is V. X coordinate and y coordinate I have to write. Okay. Here also I have to write the x coordinate. What is x coordinate? I. And the y coordinate is V. I'll need them later, okay? And this is the best way to do this question. It is very important as well, okay? Right. So first of all, write the equation. What is the equation you're going to use? V is equal to, tell me, E minus I into R. V is equal to E minus I into R. So let us put the first point, first location. You put the coordinates, right? You put in the coordinates. Tell me, Dhruvi, what is here? This is V is what? At this point, V is 6, right? You can put the value. 6 is equal to E, I have to find out, minus I value there is 0 into internal resistance. So 0 into R will be 0. You get E is equal to 6. Actually, this is a contribution from 3 cells, right? So E1 will be what? 1 cell. That is equal to E by 3. There are 3 of them, right? 3 of them, right? All of them are equal. They'll give equal, identical case only. They must have given that. Calculate the following graph shows the variation of series combination of 3 cells. Yeah, it is not given, no? If they are unidentical, they will tell you. Otherwise, it's identical, implied. Okay. Okay, right. So E, this is actually E, and E1 will be what? That will be E by 3. That's going to be 6 by 3 or 2 volt. I got the EMF of 1 cell now. I got the EMF of 1 cell now. Now I'm going to put this condition one more time. Okay. Okay. What is my condition again? I write that equation one more time. V is equal to E minus IR. Put the second condition. V is what? 0. E is what? E is 6. Correct. Minus I at that point is what? 2. Internal resistance is to be calculated. Correct. Get that 2R to left hand side. 2R is equal to 6, or R is equal to 6 by 2. That is equal to 3 volts. Oh, 3 ohm. Internal resistance is 3 ohm. This is for how many cells? 3 cells, right? So you can write. Identical, they won't. Unidentical, they won't give. They won't ask. 100% sure. They can't ask. Unidentical, they'll give only 2 cells maximum. The equation is E1 R2 plus E2 R1 by R1 plus R2. Got it? They can't ask. It's very complicated. So R is equal to, now you can write R1. R1 is equal to, this itself is a difficult question in fact. It is simple because we are doing it this way. Otherwise it's difficult. 1 ohm. Okay. R1 is equal to, it's a 3-mark question. R1 is equal to 1 ohm. Okay. One cell has an internal resistance of 1 ohm. All right. Once you are done, Right. The next part. Second part, they are asking you to find the current. Can you read the second part? For what current I will the power dissipation be maximum? Right. You can write maximum power when. Do you remember? R is equal to R. Write the equation for current. Do you remember the equation for current? I is equal to E by R plus R. I is equal to E by R plus R. So that is I. E is what? 6 divided. Oh, I can write E divided by capital R. I'm going to put small letter r plus small letter r. That is equal to E by 2R. I is equal to R. 6 by E is what? 6 divided by 2 into R is what? That is 3. It is equal to 6 by 6. That is equal to 1 ampere. So maximum current is 1 ampere. All of you got it? Let's have a quick recap one more time. This is what we learned today. First is parallel combination of cells. Look at this. Parallel combination of cells. Yesterday we derived it. We didn't write it. I'm going to write it today. So this is the equation for equivalent EMF of cells in parallel. Look at this, Anushka. Equivalent EMF of cells in parallel. E1R2 plus E2R1 divided by R1 plus R2. E1R2 plus E2R1 divided by R1 plus R2. E1 and E2 are EMFs of the cells. R1 and R2 are internal resistances of the cells. Okay. And I told you equivalent resistance is given by, you know, they are in parallel. So that must be R1, R2 divided by R1 plus R2. Then this equation I forgot to write yesterday. I write it V is equal to E minus IR. And this looks similar to Y is equal to C plus MX. All right. This equation represents a straight line, Aryan. Y is equal to C plus MX. So what is in place of Y? V. So on the Y-axis, we take V. In place of X, we have what? I. So on the X-axis, we take current. And we have a straight line. What kind of straight line? Descending straight line. Why is the graph descending? Because negative slope. How do I know? Look at M here. M is R. Or rather, minus R, right? It is negative slope. Am I correct? The slope is negative. If the slope is positive, you draw this way. Slope is negative, you draw this way. Got it? So it is negative slope. Anyway, do not worry. Graph will be given in the figure. This is the question on the paper. Third question on the paper. Okay, and I told you one more point. Look at this in series combination. If you got a number of cells connected in series, look at this. Series combination like this. 1, 2, 3, like this. These are connected in series. Effective is given by number of cells into EMF of one cell. Okay. One cell, it is 1 into 1.5. 2 cells, 2 into 1.5. 3 cells, 3 into 1.5, right? Okay. In parallel combination, whatever be the number of cells, you will count only one cell. Okay. EMF will be due to that of a single cell. Got it? Right. Now, then I told you something called maximum power transfer theorem. Okay. Proof of which is not needed. Maximum power transfer theorem tells you that the power transferred is maximum. Power transferred by the cell. Cell to what? Cell to the resistor. Power transferred by the cell to the resistor is maximum when external resistance is equal to internal resistance. External is equal to internal. All right. R is equal to small letter r. You can find the current from this. You can find the power from this. Current is what? EMF by total resistance. R plus R. Power is what? E square divided by R plus R. E square by R plus R. Got it? Right. Then we came to this, the numerical. It is question number 3 on the paper. It has come many times in examinations. You check it out. You can check it to see if I'm lying. Okay. So we have a graph of this kind. And then this location is 0,6. Why? Look at the coordinate is 6. 0,6. This location is 2,0. All right. 2,0. And you write this equation first. V is equal. This is our base equation. V is equal to E minus IR. Into this, you put the V. It is 6. E to be found out. Current there is 0. Those coordinates I'm putting are right. 0 into R will be 0. That will be E is equal to 6. But in the question they say there are 3 cells. So 3 cells, 6. One cell would be what? 3 cells, 6 volts. One cell would be E by 3. That will be 6 by 3 is equal to 2 volts. Got it? And second one, I'm putting this point now, 2, 0. Look at that. 0, V is equal to 0. And then what? This is 2, 6 minus. 6 I got from here. 6 minus 2 into R. I get internal resistance as 3. But this internal resistance is again contribution from 3 components, 3 cells, right? So one cell has how much? 3 by 3, that is equal to 1 ohm. And they are also asking in the second part, it's a 3-mark question, maximum power. When is the power maximum? Capital R is equal to small letter r. Got it? And then I write the current. They are asking for current, E by R plus R. And you can put capital R as small r or small r as capital R, depending upon what is given in the question. What is given? We got internal resistance, right? So you better replace capital R with small letter r. So what do we get? E by 2R. E value is 6. No, that is power. Current is E by R plus R, right? Ohm's law. Okay. Power, if they ask, it is E square by R plus R. E by R plus R, 6 by 6, that is equal to 1 ampere. Got this? All right. Moving to question number 11. All of you got this? Everyone online? Okay. Right. Question number 11. Question number 11. Can you see question number 11? Okay. 2 cells of EMFs. Read it. It's an easy question. Question number 11. Okay. 2 cells of EMFs. Couple of more. Make it quick. 2 cells of EMFs. EMFs 1.5 volt. Write it. EMF is 1.5 volt. And second cell's EMF is 2 volt. All right. Then internal resistance is, tell me, 0.2 ohms and internal resistance 0.3 ohm. Okay. Right. I had told you that this question could come in a numerical. Calculate the EMF and internal resistance of equivalent cell. They are connected in what? Can you please read the question? Question number 11. 2 cells of EMFs, 1.5 volts and 2 volts, having internal resistances 0.2 ohm and 0.3 ohm are connected in parallel. Underline the word parallel. Parallel. What is the equation for equivalent EMF? Do you remember? E1R2 plus, tell me, E2R1 divided by R1 plus R2. So what is my point? You have to learn that equation by heart. That is why I gave those equations in a box in the beginning. All right. Equations used here. Okay. E1R2. Put the values. What is E1R2? 1.5 into R2. 0.3 plus 2 into 0.2 divided by R1 plus R2. 0.3 plus 0.2. It is like 1.3 into 1.5 into 3, 4.5. One more place down, it is 0.45. 2 into 0.2, 0.4 divided by 0.3 plus 0.2 is 0.5. It is like 0.45 plus 0.5. This is 0.85 by 0.5. 8.5 by 5, that is equal to 1.7 volts. Did I make a mistake? E1 R2 plus E2 R1 divided by R1 plus R2. Solve it yourself. See if you're getting anything else. E1 R2 plus E2 R1 divided by R1 plus R2. Ah. 1.7, right? Second part of this question is what? R equivalent. R equivalent is what? R1, R2 by R1 plus R2. R1, 0.2 into 0.3 divided by 0.2 plus 0.3. That is 0.2 into 0.3, 0.06. 0.2 plus 0.3, 0.5. 2 places up, it is 6 divided by 50. It is divided by 12 by 100. 0.12 ohms. 0.12 ohms. Should I repeat? Okay. 0.2 into 0.3 by 0.2 plus 0.3. Read question number 6. All right, 2 more questions, take a break. Question number 6. Write any two factors. Write any two factors on which internal resistance of a cell depends. Do you remember what I told you yesterday? 4 factors I wrote, right? Right. So you can write 6th one. Internal resistance depends on, write this, nature of electrodes. Electrodes. There are 2 rods called electrodes. Okay. Internal resistance of a cell depends upon nature of electrodes, area of electrodes, distance between electrodes, nature of electrolyte. Okay. Nature of electrolyte. Okay. 4th one. Nature of electrolyte. So these are the factors affecting internal resistance of a cell. Nature of electrodes, area of electrodes, distance between the electrodes, nature of electrolyte. A cell has a liquid inside which is called electrolyte. Okay, electrolyte. There is ionic conduction inside, right? Ions would travel through the electrolyte. Do you hear me? Electrodes are anode and cathode, and ions would travel through the electrolyte. Am I correct? All right. Anyway, internal resistance depends upon all these things. Nature of electrolyte, nature of electrodes, distance between electrodes, area of electrodes. Look at the second part of the question. That's a tricky one. Let us read the question. The reading, no, capital, it is 2.2 volts, right? It is capital letter E, EMF. Let us read it. The reading on a high resistance voltmeter. The reading on a voltmeter must be a voltage, right? When a cell is connected across, it is 2.2. Okay, so voltage is 2.2. When the terminals are also connected to a resistance of 5 ohm, voltmeter reading drops to 1.8. So in case number 1, the cell is on. Case number 2, you connect it to an external resistance. Do you remember what this is? It is called open circuit. This is called closed circuit. This voltage is called EMF. This voltage is called TPD, terminal potential difference. Or there's an easy way. Out of the 2 voltages, smaller one will be TPD. The bigger one will be EMF. Yesterday I told you EMF is the maximum you can get, right? So obviously it is 2.2, right? In the question, there are 2 voltages. First thing you have to do is to identify which one is terminal potential difference, which one is electromotive force. Okay, so let us go on reading. Can you read it again? The reading on a high resistance voltmeter when a cell is connected across it. Readings on a high resistance voltmeter. You can draw the figure, only the voltmeter. This voltmeter reads how much? 2.2 volts. This is called an open circuit. Open circuit. Why? No external resistance is connected. Correct. If no external resistance is connected, you are connecting a voltmeter alone. What you are having is EMF. So the name of the guy is, this is EMF. Let us put it there. Okay. I'm calling EMF as 2.2 volts. Second case is what? When the terminals connected to a resistance 5 ohm. Look at this. You are connecting a resistance 5 ohm. Automatically, you know something will happen. An internal resistance will develop, right? Correct. Yes. When this is called a closed circuit. For those who missed yesterday, I'm repeating this. You know, open circuit means what? Open circuit means you're not connecting anything. You simply take the cell and then measure the voltage. You take the cell, for example, the cell inside this remote, you take this cell and measure the EMF. Okay, just connect the voltmeter. All right. It is written on it, 1.5 volts. That is the maximum you could get from the cell. Got it? And it is given as 2.2. It is called open circuit. What is closed circuit? You connect an external resistance to it. Okay. Automatically an internal resistance is also there, right? Tell me, what is terminal potential difference now? They say it is 1.8 volts. Correct? Correct. And what is the relation we learned yesterday? V is equal to I into R. V is equal to, you could say, V is equal to, that is also fine. V is equal to I into R, and that is equal to, do you remember what I said? Right. E by R plus R into R. Look at the yellow current, yellow letter I. Current is E by R plus R, no? Now you know how to solve this, right? Everything is given. V is given, E is given, R is given. You are asked to find small letter R. Understood? So many times asked. So many times asked. Okay. All right. So write this. V is equal to I into R. All of you online got this. V is equal to, what is our equation? Terminal potential difference. Terminal potential difference is given by V is equal to, all right, Dolly, rest of the guys, what are you doing? V is equal to I into R. Voltage is equal to current into resistance. Voltage is equal to current into resistance. If you didn't understand, I need to help you. That's why I'm asking. V is equal to current into resistance. Okay. Let's do. Right. So what is V here? I into R. I into R. I is E by R plus R into R, right? So let us put the value. What is voltage? Terminal potential difference is 2.2. EMF is given 1. Sorry. 1.8 is equal to 1.8 is equal to, the other one is 2.2 divided by external resistance is 5. Internal resistance is this into 5. You can cross multiply. 1.8 into 5 is 9. 1.8 into R, 1.8 R is equal to 2.2 into 5, that is 11. So get this to right hand side. 1.8 into R is equal to 11 minus 9. 1.8 into R is equal to 2. R is equal to 2 by 1.8 or 20 by 18 or 10 by 9 ohms. 10 by 9 ohms. Got it? You can keep it this way. 1.1, roughly 1.1. What up, Anushka? All right. So can you see question number 7? That is a 5-mark question in your half yearly examination. Okay. 7th one. Two cells of EMF C1 and E2 and internal resistance R1 and R2 respectively are connected in parallel as shown in the figure. Deduce expressions for equivalent EMF, equivalent resistance, and potential difference between A and B. Yesterday we did the derivation, but we will do it one more time. Okay. So let us do together. Right, question number 7. Okay. If you missed yesterday, do not worry. I'll ensure that you get it. Just draw the figure. This is cell number 1, cell number 2, and they are in parallel combination. Right, draw the figure. There are 2 cells here. 2 cells here. This is cell number 1, cell number 2. Internal resistance R1, internal resistance R2. EMF is E1, EMF is E1, EMF is E2. They are connected in parallel. Then draw this current I1, draw this current I2, and tell me, there are 2 currents driven by the cells, right? First cell gives a current I1, second cell forces a current I2 out of it, it's positive, right? And they come together and flow out as I. Look at the junction and tell me, what is the total current? I1 plus I2. Okay. So let us do it. Before we start, write this on the margin. This is the equation you're going to start off with. V is equal to E minus IR. Get an equation for I from it. I'm getting this IR to left hand side. IR is equal to E minus V. Or I is equal to E minus V by R. We will need it later, okay? You can put it in a box. I wrote my equation. V is equal to E minus IR. IR is equal to E minus V. Or I is equal to E minus V divided by R. Okay. So let us write. What is the total current? Tell me, Halima. I1 plus I2. The total current here is I is equal to. I1 comes out of this. I2 comes out of this. They join together to become I1 plus I2. Right? I1 plus I2. Write it. What is I1? I1, I can write I1 from here. E1 minus I is E minus V by R. So I1 will be E1 minus V by R1 plus I2 will be E2 minus V by R2. So some of you might have a confusion. Why don't I use V1 and V2? Because it's parallel combination. Parallel combination voltage will be the same. Correct. Then let us split it. Tell me what you're going to get. E1 by R1. I'm splitting every term. E1 by R1 minus V by R1 plus. This is E2 by R2 minus V by R2. Okay. E1 by R1 minus. I'm splitting each term. E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. Okay. Right. Then what? Group the identical terms together. Let's write them together. Okay, right, yes. E1 by R1 plus E2 by R2. Then this is minus V by R1 minus V by R2. So take minus common, minus V. 1 by R1 plus 1 by R2. E1 by R1 plus E2 by R2 minus of V into 1 by R1 plus 1 by R2. Okay, so take LCM now. R2 comes here. E1 R2 plus E2 R1 by R1 R2. This is our first term. I is equal to, this is all I is equal to minus V into, what is our second box? LCM R2 plus R1 by R1 R2 or R2 R1. Now you should think of this. What do I want? I want V alone in my final equation because I need to get this back. Look at this. I need to get this form back. For that, I need what? I need V to stand alone. I need V to stand alone. For that, this bracket has to be gone. How can you get rid of the bracket? Multiply by its reciprocal. Multiply by its reciprocal. When I multiply by its reciprocal, I should do that to all the terms, right? So let us write that equation one more time with enough space to put a bracket. All right, just put some space there. E1 R2 plus E2 R1 divided by R1 R2 into, I'm leaving some space, minus, what about the last one? What about the last one? There also V into R2 plus R1 by R1 R2. What have I done? I have just written that equation one more time. You must know why we are doing this. All right, because I need to get that V alone, right? That V has to stand alone, right? All right. So see what I'm going to do. I'm going to multiply everyone with reciprocal of last bracket. Reciprocal of last bracket. Reciprocal of last bracket. Look at this, even this one with reciprocal of last bracket. Now cut the common terms out. R1, R2, R1, R2 cut. R2 plus R1, R2 plus R1 cut. R1, R2, R1, R2 cut. Finally, we have something that looks like this. This is what? I into R1, R2 by R1 plus R2 is equal to. Tell me. This is E1 R2 plus E2 R1 by this is R1 plus R2. All right. Minus of, that is V. Finally, get this V to the left-hand side. Why? Forgot to write the introduction. You should write like, consider two cells with EMFs. You should always write an introduction, okay? E1 and E2, and internal resistance R1 and R2. The currents coming out are I1 and I2. They join together to make I. Got it? You can write on your own. So V. Right. V comes to this side. This goes to the right side. E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 by R1 plus R2. Below which you can write, this is called V equivalent. This is called V equivalent. This looks like V equivalent. Got it? V equivalent. And the whole bracket looks like E equivalent minus I into this bracket looks like R equivalent. So what I got is V equivalent is equal to I into R equivalent. Got it? V equivalent is equal to I into R equivalent. All of you understood until here? Then let us write question number 1, 2, 3. Equivalent EMF. Question number 1. I am writing answer to question number 1. Equivalent EMF. What is E equivalent? You have to rewrite it, okay? Once you have done this far, you have to rewrite. What is equivalent? Tell me, the E equivalent is what? E1 R2 plus E2 R1 by R1 plus R2. So let us write E1 R2 plus E2 R1 by R1 plus R2. That is answer to part 1. They are asking you to get E equivalent. All right. I am writing the answers in green circle. All right. That is answer number 1. Okay. Shall I scroll this up? Because I don't have space. Okay. I'm writing it somewhere here. Right. I'm writing it somewhere here. Okay. Right. Sure. I'm writing the second one here. Second question is what? They're asking you to get internal resistance, right? Equivalent resistance is given by R1 R2 by R1 plus R2. I've got my second answer. Third answer is potential difference, which is V equivalent. Potential. The whole thing you have right. First one we did, it's a 5-mark question. 100% sure this is going to be there in your paper. Finish this. And the last one you can write V equivalent. The third question is to get third question. V equivalent. How to get V equivalent? E1 R2 plus E2 R1 by R1 plus R2 minus of I into R1 R2 by R1 plus R2, the final equation. This is our third answer. All right, all the green ones, the green circle ones are the answers. All of you understood this? Right. Okay, right heading series combination. Right heading series combination. Even though very rarely asked, I have to do it because it is there in the reader. Okay. Very rare chance of this coming, but I still have to do it. It is given in the reader. Oh, it's very easy as well. Okay, I'll tell you. All right. Close your book. Listen. Okay, right. This is, see this? I have a cell here, internal resistance, another cell, internal resistance. Okay, they are in series combination. Equation EMF is E1, EMF here is E2, internal resistance is R1, internal resistance is R2. All right. Okay, so, you know, in this case, I can write V as E minus IR. V is equal to E minus IR. Right. What about the first one? Across the first one, if I measure V1, how do I write it? V1 will be E1 minus IR1. Right. V1 will be E1 minus IR1. Am I correct? Similar way, if I connect a voltmeter across 2, V2 will be what? V2 will be E2 minus IR2. So what is the total voltage across these two together? It is V1 plus V2. Am I correct? I'm repeating. Look at this. First is across V1. First cell, V1 is equal to E1 minus IR1. Second one, V2 is equal to, across the second cell, V2 is equal to E2 minus IR2. Then you may ask, why can't we write I1 and I2? Ask me why. Because it's a series combination. In series combination, there is only one current. Current will be the same, right? Current does not branch. There is no second path for the current, right? In series, you know, there is only one path for the current. Same current will flow through both the cells, right? So that is why I'm writing I for both. Anyway, this is what? This looks like E1 minus IR1 plus E2 minus IR2. This is V. Now V is equal to, let us club the terms together. Look at this, E1. Tell me what? Plus, this is E2. Am I correct? Am I correct? E1 and E2 are taken together, minus I into, tell me Nidal, IR1, IR2, I into R1 plus R2. Right underneath, I can write what? Look at this. V equivalent is equal to E equivalent minus I into R equivalent. What is in place of V equivalent? It is V. What is in place of V equivalent? E1 plus E2. What is in place of R equivalent? R1 plus R2. That's it. Understood? Direct and easy. All right. Series combination is very, very easy. Okay. Let us do it together. Right heading, series combination. Let us write series combination. All of you online understood? Series combination. Since I forgot to write introduction in the last case, I'm not writing this time also. Okay. Right. All right. Right. Anyway, you can write. There will be uniformity. That's why. Right. This is E1. This is E2. This is R1 and this is R2. And across the first one, you connect a cell or EMF V1. Across the second one, you connect a voltmeter. It is V2. And both the cells drive the same current. So we have two cells. Two cells. Two cells. Okay, so first you write, you're starting off with equation for V. What is the equation for V? E minus I into R. V is equal to E minus I into R. Okay, V is equal to R. V1 is equal to E1 minus IR1, equation number 1. V2 is equal to E2 minus IR2. V1 is E1 minus IR1. V2 is E2 minus IR2. You're going to take them together. Therefore, V, the total voltage is equal to V1 plus V2. That is E1 minus IR1 plus E2 minus IR2. So, E1 plus E2. I took these guys together, minus of I into R1 plus R2. This is V. Right below which you write V equivalent is equal to, this is E equivalent minus I into, this is R equivalent. V equivalent is equal to E equivalent minus I into R equivalent. Let us rewrite them. First you write E equivalent. E equivalent is what? Number 1. E equivalent is E1 plus E2. I had told you beforehand. In series combination, you'll just add them up, right? E1 plus E2. Okay. In parallel, in the second case, internal resistances, R equivalent is equal to R1 plus R2. R1 plus R2. All of you got this? Now, look at this. Before I do the next topic, I'll tell you, look at this. Imagine I have n cells like this. It's a special case, n cells like this. What is the equation for EMF? One cell is E, two cells 2E, three cells 3E. Why do you look surprised, Baris? N cells it is Ne, right? N cells it is Ne. So effective EMF is Ne. For n cells in series, effective EMF is Ne. And imagine one of them is wrongly connected. Wrongly connected. Wrongly connected means, look at that. Negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. But the last one is negative, positive, right? Correct. So if one of the cells is wrongly connected, what will happen? It will cancel one more cell. Okay. So the effective will be Ne minus 2E. Ne minus 2E. Why? Because when you connect one cell in wrong connection, it is in fact cancelling one more cell. This cell will cancel this cell out. Understood? That is why you write Ne minus 2E. For example, if they say like 7 cells are connected and one of them is wrongly connected. So what will be the effective EMF? 7E minus 2E. That is equal to 5 times E. Understood? But even then, Be it right connection or wrong connection, internal resistance will be the same, 7R. For first one, it is small letter r. Second one, small letter r. Third one, small letter r. It is eventually internal resistance will be what? 7 times small letter r. 7 times small letter r. Got it? Be it right connection or wrong connection, internal resistance will be what? You know, the sum of internal resistances. Okay. But when you connect them in opposite directions. Yeah, right. So the net will be what? Ne minus 2E. Ne minus 2E. Got it? Now, we'll write it later, but I'm going to tell you Kirchhoff's laws now. Kirchhoff's laws. Okay, this is actually the most important and the most difficult part. Last year, I had to take this 4 or 5 times in class. I'll do it anyway. Okay, Kirchhoff's laws. We'll be using special techniques to solve questions here, and you're going to find it very easy once we are done. All right. So there are basically 2 laws which help you to solve electrical circuits. Okay, electrical circuits. First one is called Kirchhoff's junction law or Kirchhoff's current law. Kirchhoff's junction law, KJL or KCL. Kirchhoff's junction law or Kirchhoff's current law. Look at this. It's very simple. Imagine you have a junction. This junction is also called a node, NOD, node. Okay. And there are few currents coming in and few currents going out. Look at this. One current I1 is coming in. Another current I2 is coming in. Then we have like few currents I3, I4 and I5. They are all going out of the junction. All right. Think of it this way. Just imagine water is flowing in. Water flows in through this pipe, through another pipe, and water flows out through these pipes. What can you say about this? The net inflow of water must be equal to the net outflow of water. It is common sense, right? Because water cannot stop flowing. Water cannot get accumulated anywhere at a junction, right? So if water is flowing in, for example, if this is 3 liters of water, if this is 5 liters of water, tell me 3 plus 5 is 8, right? If this is 2, if this is 4 liters, it is certain that this is 2 liters. Because 2 plus 4, 6, 6 plus 2 is 8. If 8 is coming in, 8 must go out. Am I correct? Am I correct? I'll repeat, you know, total incoming amount of water must be equal to the total outgoing water. Right. This can be applied to the case of electric current. Now replace water with electric current. I can say the net incoming current, I1 plus I2, net incoming current must be equal to the net outgoing current. All right. Because current is helpless. It cannot stop flowing. If it is flowing in, it must be flowing out. All right. The current is flowing in, that must flow out. It cannot stop here. All right. Okay. So the net incoming current must be equal to net outgoing current. So let us get those guys to the left-hand side. I1 plus I2. I3 comes to left side. So it is minus I3. Right. Plus I4 comes to left side. Minus I4. Plus I5 comes to left side. Minus I5 is equal to 0. All right. This is like sum of currents, right? Sum of 5 currents, right? Sigma I is equal to 0. Algebraic sum of currents reaching any junction is equal to 0. Then you may ask why the negative sign. Plus sign means incoming current. Minus sign means outgoing current. That's it. It's like a sign convention. Got it? So the statement is this. The algebraic sum. Algebra. This is called algebraic sum of currents reaching a junction is equal to 0. The algebraic sum of currents reaching a junction is equal to 0. Understood? There are very complex numericals about this regarding KCL, but they won't be asked in board examinations, only for competitive examinations. All right, that to JEE mains only, not even for NEET. Understood? But KJL based numerical is there, very simple ones. I'll do them in class. Very simple one, I'll show you. But KVL, second one is very important. There are many questions on this. We'll do one full paper on it. I've taken a paper with 13 questions or 14 questions, as you can see. I think there are 14, right? 14 or 13? 13. All 13 are unique ones. Okay, they are all from previous papers. They might do 1 or 2 in school, but we have to do all of them. Okay, there are 30 or 40 questions on this, but I've taken the unique ones there. Got it? All right. So this is Kirchhoff's junction law. Look at this. What is Kirchhoff's junction law? The algebraic sum of currents reaching a junction is equal to 0. Let me show you something. You know, this I1 may be written as Q1 by T, right? current is equal to charge divided by time. What is the definition of current, Madan? Current is charge divided by time. Correct. So Q1 by T, tell me Halima, plus Q2 by T, then plus minus Q3 by T, plus minus Q4 by T, plus minus Q5 by T is equal to 0. Cut all the T's. Common, no? So you can also say sigma Q is equal to 0. This is not there in the reader, but you must know this. What is the question? Kirchhoff's first law is in accordance with option A, law of conservation of charge, option B, law of conservation of energy, option C, law of conservation of momentum, option D, law of conservation of angular momentum. One of the most repeated questions, law of conservation of charge. Kirchhoff's first law is law of conservation of charge. The net incoming charge must be equal to the net outgoing charge. Got it? Because second law is law of conservation of energy. I'll prove it. Law of conservation of energy. All right. I'll tell you one previous question from KJ. Look at this. I have like two currents coming in and one current goes this way, another one this way, another one this way. And they are saying like this is 1 ampere, this is like 2 amperes, this is like 1 ampere, and this is like 4 amperes. Oh, this is like 4 amperes. This is like 2 amperes. What is this current? That is the question. How to find it? 1 and 1, 1 and 2, they join together, right? 1 and 2 join together, this becomes what? 1 plus 2, that is 3, right? And 3 and 4 join together, 3 plus 4, 7. Correct. 3 comes this way, 4 comes this way, 7, right? 7 flows out. It reaches the junction, 2 goes this way. 7 minus 2, this will be what? 5. Understood? Understood? Such simple questions can come from KJL. That's it. Okay. It's a repeated question, so many times asked in different papers. Okay. They'll give you a figure like this and you can easily identify. Just know one thing, incoming current must go out of the junction. Got it? So Kirchhoff's junction law, this is Kirchhoff's junction law. Kirchhoff's voltage law, I'll tell you. Before that, we'll write this. Okay, start writing. All of you got this? Write a note on cells first. Write a note. Write a note on cells first. All of you online? Everyone? Yes. Right. Okay, so just write this note. If n cells are connected in series, with one of them wrongly connected, draw the figure if you want. If n cells are, I don't draw the internal resistances there. Okay, everyone has an internal resistance. If n cells are connected in series with, last year it was asked in MCQ. I didn't expect it because like last couple of years I didn't teach this because it's a competitive examination question, but it was asked last year in a school paper. All right. Yeah. Last year. No, half yearly. Last year, school. If n cells are connected, I used to teach this every year until last year, but then I stopped because it is not asked anymore. But all of a sudden they asked last year. I don't know why. Okay, so if n cells are connected in series and with one of them wrongly connected, you can write E equivalent is equal to n cells are connected in series. So effective is Ne. Correct. N cells in series, effective is Ne. All right. One of them is wrongly connected means it will nullify one more cell. Okay. One cell in wrong connection will cancel one more cell. So 2 cells are gone effectively. Understood? That is why we take Ne minus 2E. Put this in a box. E equivalent is equal to Ne minus 2E. But R equivalent is still what? It is NR. Internal resistance, be it in right connection or wrong connection, internal resistance is always addition of all the resistances. R plus R plus R plus R plus R plus R, NR. Correct. So if n cells are connected in series, one of them is wrongly connected. If n cells are connected in series, one of them is wrongly connected. Effective is given by Ne minus 2E. Got it? Because one wrong cell will cancel one more cell like this. Okay, they are gone with each other. So effective is Ne minus 2E. But internal resistance will be what? It would still be NR. Got it? Got it? Right. If say they say like, 5 cells are there. One is wrongly connected. 5E minus 2E, that is 3E. But the effective resistance will be 5R. Got it? All the internal resistance together. Got it? Right. Okay. Now write this Kirchhoff's laws. Right heading Kirchhoff's laws. Right heading Kirchhoff's laws. These are actually laws that help us to solve complex electrical circuits. Kirchhoff's laws. Number 1, Kirchhoff's current law or junction law. Kirchhoff's current law or junction law. KCL or KJL. Kirchhoff's current law or Kirchhoff's junction law. Kirchhoff's current law or Kirchhoff's junction law. Kirchhoff's current law or Kirchhoff's junction law. Okay. Now you can write the algebraic sum of, we are writing the statement first. The algebraic sum of currents reaching any junction is equal to 0. The algebraic sum of currents reaching any junction is equal to 0. The algebraic sum of currents reaching any junction is equal to 0. Draw this figure. So we have few incoming currents, few other outgoing currents. It doesn't matter how many. You can even write I1, I2, I3 as incoming, I4, I5, I6 as outgoing. Got it? Few incoming currents and few outgoing currents. Got it? So you can write, let I1 and I2 be incoming currents and I3, I4 and I5 be outgoing currents. Let I1 and I2 be the incoming currents and I3, I4, I5 be the outgoing currents. Okay, then write I1 plus I2. The net incoming current, right, should be equal to what? I3 plus I4 plus I5. I1 plus I2 is equal to I3 plus I4 plus I5. Okay. I1 plus I2 is the total incoming current. The current coming to the junction must be equal to current going out of the junction, right? Now get this to the left-hand side. I1 plus I2. Then what? I3 will come to left side plus minus I3. When I3 comes to the left side, it becomes minus I3, right? Plus I4 comes to the left side, minus I4. I5 come to the left side, minus I5 is equal to 0. So we have basically like 5 currents whose sum is equal to 0. Correct. So two are positive currents, which means they are coming in. And 3 are negative currents, which means they are flowing out, going out, right? So finally you can write, therefore, sigma I is equal to 0. Write the sigma I is equal to 0. Write this. This is the meaning of algebraic sum of currents reaching a junction is equal to 0. Sigma is summation, adding. Okay. Sigma is equal to 0. Okay. Right. Okay, finished? All right. Now write a note. All of you online finish this, or anybody wants more time? All right, Hadia, thank you. Previous slide. Okay. I won't start KVL. Next class, I'll finish KVL. Okay. Everything. Almost chapter will be completed by next class. Okay. Kirchhoff's voltage law. Voltage law. And the numericals. 100% sure there will be a 3-mark question. I promise. If you simply attend the class, you will get it. Boards or school. 100% sure. Okay. Just attend the class. That's it. Tell me when done, Trisha. All right. Now look, write this. Not Q1 by T plus Q2 by T plus minus Q3 by T plus minus Q4 by T plus minus Q5 by T is equal to 0. Nothing. I have written every current as charge by time. Charge by time. So first current I1 is Q1 by T. Second current I2 is Q2 by T. No, same time. We are taking it over same time, no? Same time, over the same time. All right. I'm finding time taken to reach the current, I mean, the distance is the same. We are finding per time. Yeah, you're finding per time. All right. So all the T's are cut. You're getting what? Q1 plus Q2 plus minus Q3 plus minus Q4 plus minus Q5 is equal to 0, which in turn means sigma Q is equal to 0. Then you can write, thus, mark it as very important, this statement. Thus, KJL, Kirchhoff's junction law, is in accordance. Obeys. Kirchhoff's junction law obeys. Law of conservation of charge. Very, very important. Many times asked in examinations, law of conservation of charge. Okay, Kirchhoff's junction law is in accordance with law of conservation of charge. Okay. All right. Okay. Kirchhoff's junction law is in accordance with law of conservation of charge. Finish this. Write that question also. Draw the figure. Find I. Find I. This is 3 amperes. First one is 3 amperes. This is 2 amperes. That is 1. This is 4. Just look at the junctions and give the signs. That's it. Okay, give the values. Junction law. Okay. Tell me, first of all, tell me what 3 and 2, they come together, right? 3 comes to this side and 2 comes to this side. Altogether, it is what? For the answer, I'm using green color. Okay. 3 plus 2, it is 5 amperes, right? Okay. This one. You have to find out. Its direction is coming out. It's going out. Coming out. Okay. Right. So tell me, 5 is what? 5 is coming to this junction. Then 1 goes out of it, right? From 5, 1 goes out this way. So this must be 4 amperes, right? Then what? This 4 is coming to the junction. This 4 is coming to the junction. Finally, it flows out as 8 amperes. Answer is 8 amperes. Yeah, that's a 1 mark question. It's a previous one. Okay. Which one? Yeah, minus. So if it's going out, you have to minus. If it's coming in, that's plus. You have to add it. Okay, right. So basically, like 3 rupees and 2 rupees, 5 rupees altogether. Now you lost 1 rupees on the way. Then you got 4 rupees with you, and then another 4 somebody gave you. 4 plus 4, 8 years with you. That's it. Got it. So just write down the statement of the next one. That's it. We will wind up for the day. Tell me when this is finished. All of you finished this? Oh. Oh, this one. Finish this? Okay, just write the statement. We will explain it tomorrow. Oh. Which one? Which one? This is 3 plus 2, 5, no? 1 went this way. 5 minus 1, 4, right? Then add it to that, another 4. So altogether 8. Okay. Write this. Number 2, Kirchhoff's voltage law. Just write the statement because I've got 5 minutes left. Kirchhoff's voltage law. I'll explain it in the next class only. Kirchhoff's voltage law, also called loop law, also called mesh law. Mesh. KVL. Kirchhoff's voltage law. Loop law or mesh law. Just draw the figure. Do not follow whatever is taught in school. Just follow whatever I tell you. That's it. Otherwise, the question will be very difficult. Okay. All right. Because over the years, they are following, whichever school they are following the way it is directly given in the reader, which is very complicated. All right. Yeah. But there is easy method to do this. All right. With which you can solve even the most complicated question on the reader. I'll show you. We'll do that in the next class. But I'll just write the statements. Just name the junctions also. A, B, C, D, E, F. Kirchhoff's voltage law or Kirchhoff's loop law or Kirchhoff's mesh law. The algebraic sum of EMFs in any loop. EMF means electromotive force. The algebraic sum of EMFs in any loop is equal to the algebraic sum of potential differences across all the resistors in the loop. The algebraic sum of EMFs in any loop is equal to the algebraic sum of potential differences across all the resistors in the loop. That is, sigma E is equal to, sigma E means algebraic sum of EMFs. Sigma IR. Sigma IR means algebraic sum of potential differences. Okay. Yeah, I1 R1. But there is an easy way to do it. Okay. This is the equation. Statement is algebraic sum of EMFs in any loop is equal to the algebraic sum of potential differences across all the resistors in the loop. That is, sigma E is equal to sigma ER. This is law of conservation of energy. I'll prove that in the next class. Law of conservation of energy. Kirchhoff's first law was what? Law of conservation of charge. Kirchhoff's second law is what? Law of conservation of energy. So shall we wind up for the day?